Okay, so category theory basically deals with two things. On one hand, it abstracts a lot of sort of very basic notions that we encounter all over maths. And on the other hand, more specifically, the reason why it was invented was to give some rigorous meaning to the statement, oh, this homomorphism or this isomorphism is canonical or natural, meaning that somehow it doesn't involve any choices and has the same formula for every object you're considering. But like, I don't know, I've heard the sentence before I learned category theory, and it annoyed the shit out of me just because what does it mean it is natural? And category theory set out to describe what that exactly means, and yeah, did a pretty good job at it, I think. And I guess we'll start off by defining the basic notion of category theory. By the way, can you all read what I'm writing? Okay. So the basic object of category theory is, surprise, surprise, a category. We call the category C here. And a category consists of the following data. It consists of a class ob C called the objects of C. And for every pair of objects A and B, we have a set more AB called the morphisms from A to B. And we have an operation circle from, well, suppose we have 3 objects, then it goes from more BC, more AB to more AC, called composition. Basically, we have a morphism from A to B and a morphism from B to C, and there's some way to compose them to get a morphism from A to C.
Sorry, what is this subscript under the more? That's a C, right?
Well, that's just a C, meaning we are working in the category C.
Oh, okay, yes.
Yeah, by the way, the reason I said a class of objects here is just that usually we want a set there, but sometimes you just have too many things. So in a minute, we'll discover that set is a category, the category of sets. And if you imagine the set of all sets doesn't exist, it's sort of too big to fit into a set. So it has to be a class, but that's just some technicality, and usually you just get away with working with it like a set. And
for morphisms, you usually get set.
I'm sorry, what?
For morphisms, you usually get set. So the morphism.
Yes.
I mean, it mostly won't matter.
Yeah, to be fair, it's called locally small if the home sets are actually sets. But we'll just assume that every category is locally small, just because everything else is just hell to work with. And yeah, we have small condition on our things, on our data. Namely, we want the composition to be associative. and can't postpone it any longer, I will have to break out some diagrams. Yeah, by the way, in category theory, everything is done using diagrams. And when I say a diagram is commutative, it just means if I compose everything in any way possible, then things should be the same. So I have 3 objects, A, B, and C. No, 4 objects, A, B, C, and D. Now magically written in uppercase for no reason whatsoever. And I have a morphism from A to B, and a morphism from B to C, and a morphism from C to D. And then I can compose first F and G. So this is G after F. Or I can compose first G and H to get H after G. And the statement is that this commutes. That means that, well, if I go along this path and then along this path, you get the same as if you go along this path and then this path. Or if I really want to write it out,
sorry, we can't see your mouse moving. So if you want to indicate something, I guess.
Okay. Yeah.
Draw.
Okay. So doesn't matter if I first go along this path and then along this path, or first along this path and then along this path. And written out, this just looks like H after G after F is the same as H after G after F. What you usually write down when you suppose, or when you want to have something be associative.
Yeah, so it's called a commutative diagram. I'm sorry, it's called a commutative diagram, but it's really just a property of the associativity, right?
No, the thing I drew down here is called a commutative diagram. This has nothing to do with associativity. It just, commutative in this case just means it doesn't matter which path you go, you always get the same.
Yeah, but is it not correct that it's just the associativity condition, right? What you've written down.
Yes, of course.
Okay, but it's called commutativity, okay.
This diagram, no, it's just a commutative diagram is a general tool I use for showing properties. And this particular one is a pictorial representation of associativity.
Okay.
We'll get a bit more, I hope it will get a bit more clear when I write down the one for the second condition. Namely, we have for each object, there is at least one morphism, or a particular morphism called IDA, and that goes from A to A, and it satisfies 2 conditions, or it satisfies 1 condition. Well, it should be the identity morphism. So if you compose it with any other morphism, it shouldn't change that morphism. So in the diagram, we could say if we have another morphism from B to A, and we do the identity of A, we execute that one after our morphism. That should just be the same as the morphism itself. Similarly, the same situation when we reverse our arrows. So this means IDA after F is equal to F. And here we want F after IDA is equal to F. So basically, we have function composition and we have identities. And yeah, this sort of speaks to the fact that, yeah, in math, we're always looking for abstraction, and we have things like groups that abstract the notion of addition of numbers or multiplication of numbers, or like topological spaces that abstract the notion of continuity and closeness. Categories abstract the notion of function composition.
Can I ask one more thing about the diagram, the top one?
Yes.
Yeah, so the arrow going from B to D, you wrote H following G, but should that be the other way around? Does that not matter?
That matters very much. And we always interpret the circle to mean after. So we have H after G,
okay.
which...
Yeah. Okay, thanks.
Okay, so the slogan is categories abstract function composition. And yeah, sort of a general trend in category theory, or like when you're dealing with stuff that should be described categorically, the morphisms are always the sort of more interesting object, or the more interesting thing to consider. So very important thing whenever a new kind of algebraic structure, or generally a new kind of thing is introduced, ask, what are its morphisms? And now comes the section that everybody looked for, the example section. And we're now going to define a whole lot of categories. And they all have sort of cryptic names that came out of, well, basically people wanting to abbreviate stuff, and then it just became weird. So first one, not very hard, set. So we want to describe set. We have to do two things. We have to describe the objects and the morphisms. So what are the objects of set? And yeah, it's the class of all sets. Okay, and what are the morphisms between a set A and a set B? Well, that's just the functions from A to B. And yeah, composition is just composition. And in a similar way, the mathematicians probably know where this is going. A lot of categories are just built up out of, we have a set and we have some sort of special structure on it, like a group structure or topology or a sigma algebra or a ring structure or whatever. And then we have maps that sort of respect that structure, like group homomorphisms, continuous maps, measurable maps, ring homomorphisms. And at some point, it was shown that sort of a composition of these maps still respects that structure. And that is exactly, well, basically what a category is. So second category, GRP, abbreviation for group. Objects are groups, or let's say the class of all groups, and the morphisms from a group G to a group H. Well, that's just the group homomorphisms. And yeah, the composition of two group homomorphisms is again a group homomorphism, so that really defines a category for us. Similarly, I'm just going to mention them. We have abelian groups, rings, fields, k-vector spaces. Yeah, I don't really know how to write this. Finite dimensional k-vector spaces. A modules, and yeah, whatever. So sets with additional structure, and between those objects, the morphisms are just the homomorphisms of that structure. Another thing that I also mentioned, topological spaces. That's called top. Because topological spaces are always called top spaces. And a morphism of topological spaces between two topological spaces X and Y is just continuous maps. Yeah, same thing could be done for measurable spaces and measurable maps. And yeah, I guess this is sort of the mathematical motivation. We've noticed this pattern and this is the abstraction, but there are also sort of just categories that are interesting within category theory, and I'm just going to introduce them really quickly. We have the empty category, where the class of objects is the empty set. And well, do we have a set of morphisms for every object in the empty set? Yes, we do. So category. And then an interesting example.
I'm sorry, can I interrupt?
Yes.
That topological spaces, how much structure do these topological spaces have? Are we just talking about like the bare basics, set theoretical topology, or also? Yes. Okay.
Oh, I think I need to get some power for my laptop. So topological space just means it is a set, I have a topology on it. That's it. Nothing more. But of course you can say like compact topological spaces, connected topological spaces, again with continuous maps. Or if you really wanted manifolds with smooth maps.
Yeah, okay, yes.
Those are two examples of manifolds. Sorry, of categories. And yeah, now for an example that may seem a bit weird or uninteresting. We have, yeah, we have a partially ordered set, X with the relation smaller than or equal to. We can also make that one into a category, namely by defining the objects of that category to be the elements of X. And then we say the set of morphisms between, well, A and B is equal to, and now we just have a singleton set containing whatever, exactly one element. If A is less than or equal to B, or being the empty set, if A is not less than or equal to B. And then we sort of have composition to be, we just then have composition, like if you have the one element of one home set and the element of another home set and you compose them, you get the element of the target home set. Otherwise, you're defining a map on the empty set, which is empty. So this is sort of boring. And of course, the identity is just that thing. And sort of the category axioms, namely that the composition is well-defined and associative, and that we have an identity just corresponds to the axioms for a partially ordered set. Namely, this here is reflexivity, then the associativity of the composition is transitivity, and what was the third property? Asymmetry. I don't know.
So whether when you have an arrow between A and B and one between B and A, then you somehow only have you can compose them, then you got another one between A and A.
Oh yeah, but that then is the identity, so that's an isomorphism. And well, the last one, oh, not really even the last one. If we just take any set X, then we can make X into a category, namely by saying that that category has as object the element of X, and as the morphisms between two elements just being like the set containing anything if A is equal to B, or the empty set otherwise. So we literally only have one isomorphism per set and no morphisms whatsoever between any different two objects. So this is sort of the minimal category made out of X that really is a category, and it's called the discrete category. And then we have the opposite category. So if C is a category, we can define C-op by saying that the objects should be exactly the same as the objects between the objects of C. But now the morphisms sort of reversed. So the morphisms of C-op between two objects X and Y are the morphisms in C between Y and X. And yeah, composition of two morphisms F and G is the same as the reverse composition in C. So what this op does is basically it reverses all of the arrows, leaves everything else intact. And this is sort of just a purely syntactical device because sometimes we will encounter functors that reverse the arrows, and then we can just say, okay, reversing the arrows is just the same as going to the opposite category, and then it doesn't reverse the arrows anymore. Yeah. And was that everything? Oh no. Lastly, we have cat. What are the objects of cat? Well, those are these small categories. Yeah. By the way, category is small if the objects is a set. So when we go back, set is not small, group is not small, app is not small, ring is not small, field is not small, k-vect is not small, top is not small. If we have a poset, then that category is small. If we have a discrete category, that is small. If C is a category, if C is a small category, then C-op is also small. Yeah. Curious question. What are the morphisms between two categories? Or put differently, I've now introduced a new kind of algebraic structure. So now you have to ask me, oh, so what are the morphisms? And I say, I'm glad you asked. Oh. Yep, the opposite category of cat is dog, correctly. So, what are the morphisms between categories? They are called functors. So, let's C and D be categories. And now I'm going to, again, do a bit of a category theory definition. So you notice in like algebra, it's always a blah, blah, blah is, and here it's always a blah, blah, blah is given by the following data, or consists of. this is going to stay the same. So a functor from C to D, and note that I'm always using this function notation for stuff. A functor from C to D is given by the following data. We have, well, category consists of two things. So our functor had better do stuff with two different sorts of things. Namely, we have to do something with the objects and something with the morphisms. So we have for each object for each object we have to have an object f of x that is now an object of D. And for every morphism, in the category C between two objects x and y, we have to have again a morphism f of f that is now in the category D between the objects f of x and f of y. And again, we have some conditions. And again, these conditions have something to do with the conditions we had on the data that defines a category. Namely, we have the identity that needs to be a special case, and we have to do something special to function composition or to composition. Namely, f applied to the identity should again be the identity, but now at f of x. And secondly, if we have a function composition, then f applied to that composition should just be the composition of f applied to the two functions or to the two things. If we want to write this in diagrams, then we have the first rule just means that identity is mapped to the identity. And the second rule means that, well, we have x, y, and z. G, f, f after g. Then this diagram gets mapped to, well, f of x, f of y, f of z, f of g, f of f, and f of f after g, and that this diagram still commutes so that f of f after g is the same as the composition of these two arrows here. So what a functor does is it turns a commutative diagram into a commutative diagram. And in fact, we could even say that a diagram is a functor. Yeah, I don't know how much I want to expand on this notion. So what are examples of functors? And this is really all of maths because, yeah, ultimately this is something that helped found category theory. The notion that, oh, these things all behave the same, they are all functors. Okay, first thing is the image functor. So we have a, we define a functor from set to set. We have to do two things. We have to say, what does it do on the objects? What does it do on the morphisms? So if x is a set, then f of x is the power set. And if f from x to y is a function, then we say that f of f should be a function from the power set of x to the power set of y, meaning that it should map any subset of x to a subset of y. And since I've already told you that we call this the image functor, a natural thing would be to send a to f of a. So the set of, well, f of x for x and a, the image of a under f. And yeah, it's a functor just because, yeah, I don't know, something one, if ever, shows at beginning of set theory. Secondly, pre-image. And this is a bit more interesting because this is where the opposite construction comes in, because the pre-image functor doesn't go from set to set, it goes from set op to set. So we have a set x. What do we define f of x to be? Well, again, we take the power set. And okay, so if we have a morphism in the opposite category from x to y, that is the same as a function from y to x. And now we want f of f to be, well, a morphism now in set from px to py, meaning that we sort of want to reverse the direction. We have a map from y to x, but we want to map subsets of x to subsets of y. What do? We map A to the pre-image of A. And again, the fact that it's a functor, well, the pre-image under the ID of A is just A. And if we have F inverse of G inverse of A, that is the same as G after F pre-image A, something like that.
I could also define this functor going from set to set op, couldn't I?
Yeah, sure.
Okay, I guess it doesn't make any big difference.
Doesn't make a big difference, right? Okay, we can define.
Sorry, so that went a bit fast. I was really writing a lot. So could you give a quick overview of everything that we've written down? I mean, just from the pre-image part. Just from the
okay, the pre-image part. We have a map. Okay, we have two sets, x and y, and we have a map from x to y. Okay, should probably say from y to x. And now what this pre-image thing does is we have a subset of x, and we want to make a subset of y out of it. So we just say every element in y that lands in our subset of x when we map it with f. So x in y such that f of x lies in A. Just the pre-image of sets.
Philip, I'm not sure whether you explained this or not already, but why is it that opposite category should always exist for a category?
Well, we just defined it here.
No, but that's for...
It's for any category. And we can just check really quickly that it's indeed a category, just by showing that it satisfies like associativity and identity.
Okay.
And then...
So, but this does imply that a dual category will always exist, basically.
What the opposite category, yes.
Yeah.
Because like opposite literally just says, okay, I know it's a function from x to y, but I sort of pretend it really goes from y to x. It's just the, it doesn't really do anything. It just labels sort of beginning as end and end as beginning.
Okay.
Okay, now for something more algebraic, or I don't know, algebraic, we have the hom functor. And yeah, the notation is really a bit shady on that one, because what I've been calling more is quite often also just called hom, because like morphisms, homomorphisms, and usually our morphisms used to be called homomorphisms. So yeah, this is called hom functor, even though it is the morphisms. So let's see be a category. And then we can define, let x be an object of C. And then we can define the functor h upstairs x from C to Z by just saying it should act on other objects as, well, it associates with an object y the morphisms from x to y. And what does it do with maps? Well, okay, so if f is a morphism from y to z, then hx of f should go from, well, hx y to hx z, but we wanted this to be the morphisms from x to y, and those are the morphisms from x to z. So I draw it here. Yeah, if we take an object in there, we are basically in the situation that we have a morphism from x to y called g, the morphism from y to z called f. And what do? We just compose the two. Yeah, f after g. Okay, this is again a morphism. The functor laws just basically come from the category laws in C. This is also called the left hom functor. And conversely, we can define the right hom functor. And that one now goes from the opposite category to set, where we basically just reverse the arguments to more. So we have hx of y is the morphisms from y to x, and hx of the morphism f is just the thing that takes g and precomposes with f. So sort of the dual notion, whatever that might mean. Okay, then, I don't know, another example, adjoining a set. I don't know how many of those I'm going to do. So
which one of these is covariant and which one is contravariant?
okay. We don't do that kind of terminology here. every functor is covariant by definition, because every functor maps a map from x to y to a map from f of x to f of y, and sort of respects composition in the covariant way. And the way we model contravariant functors is by saying that it is covariant from the opposite category. That's why we have this thing.
But I still am back to my old question. Like, I understand that an opposite category will always exist, but what is the intuition behind it? Like, how are you supposed to interpret it?
The intuition, we just pretend that the morphism goes the other direction by just saying direction of morphisms, like it doesn't really matter.
But it does
Well,
matter, because we get like different things, right? Like we get contravariant, covariant vectors now.
Well, this doesn't have anything to do with vectors, but because I defined the composition in the opposite category to be the sort of reversed notion of the, okay, this is maybe getting a bit into the weeds, but the old terminology was that we have covariant functors and we have contravariant functors. Covariant means that a function composition turns into the, well, function composition like we saw above. And contravariant means that it sort of reverses the order. And how we can combat this is by just saying that, well, okay, we can define a category where we just define another notion of function composition that just does stuff in the other direction. And then we have, well, G after F, in some weird way gets turned into G after F on this side here. So then we haven't reversed the order. And that is sort of the trick to make our contravariant functor covariant again. So that we don't have to talk about variance because everything is just covariant.
Okay, question. Could we go back to the home functor real quick and see what it precisely does? So I see that it maps G to F after G. Is that kind of the essence of the object, or not the object, but like the thing?
Yes. I don't know, it's not really that instructive, but like in commutative algebra, we often had the question, we have short exact sequence, and then if we sort of take homomorphisms from A to some object D, oh, that is probably even completely wrong. Okay. D to B, D to C. Well, is that thing here still exact? Where we sort of have here some, I don't know, where we just post-compose all the time. And then at some point in commutative algebra, we had the statement that, oh, the left hom functor is exact. Or I don't really know which one it was. Meaning that, yeah, this thing is then still exact. That is why I'm introducing this. It doesn't really have that much concrete meaning, especially not in physics.
Well, no, I don't necessarily mean concrete. I'm just trying to see what it does. Why is it so interesting and fundamental that you're telling us this now? What does it do in abstract terms?
Interesting is basically because of the Yoneda lemma, meaning the precise statement of we can completely describe a category by its morphisms, or we can completely describe an object by the morphisms that emanate from it. Namely, we can completely describe x by h to the x, or by the morphisms that go to it, meaning we can completely describe x by h lower or downstairs x. That's basically everything. And also meaning basically that this more thing I introduced, that this thing is indeed sort of a functor in its first argument and a functor in its second argument. Okay, other examples, I don't think I'm going to write them down, but like if you have a ring and you adjoin a set, that gives you a functor because every ring homomorphism and every map of sets induces a ring homomorphism between the adjoints. Then localizing is a functor, localizing of modules. And yeah, this one might be interesting. The derivative is a functor. Yeah, okay, so we consider the category of, oh, we can just say, okay, our category C has its objects, open subsets of Rn for n variable, and the morphisms are just the smooth maps. Then we can define, oof. Okay, can't really do it like that. So the objects are not open subsets. They are pairs of things where U is an open subset of some Rn and X is an element of U. And then we have morphisms from, well, XU and YV are the sets of F, are the sets of smooth maps from U to V that map X to Y. So in a more general setting, you would call these things pointed manifolds. And yeah, we can define a functor on this category by saying that, well, with with a set, with a pair XU, we are associating, well, just the Rn where this is in. And with a map that goes from U to V, mapping X to Y, we associate the derivative from Rm to Rm. Yeah, just H is mapped to the derivative of X in of F in X into the direction H. This is also a functor because, well, if f of x is equal to y and g of y is equal to z, then we have f of g after f is equal to derivative of g in f of x into the direction of the derivative of g at x. into the direction H, I suppose. Chain rule. So by somehow encoding the point at which we are evaluating our stuff, we've turned the chain rule into the statement of the derivative as a functor. Nice, I guess. And yeah, now we can again some weird examples from category theory. Well, I guess exactly as weird as the home functor, the identity functor. And again, it's a bit of a boring example because it doesn't really do anything. We define capital ID of an object X to be that same object X. No, the Leibniz rule is has to do with multiplication, and multiplication isn't really a categorical notion yet. No. Well, and if we have a morphism F, the identity functor just turns F into F itself. So it does exactly what you would expect the identity functor to do, well, for any category C. And then we have the constant functor, which I guess it's even more boring, but we have I have to introduce it now because we're going to use it a bit later. Yeah, again, for any category C. Yeah, let's let X be an object of C, and okay, should probably have two categories, C and D, and we say X should be an object of D. Then we define F from C to D as, well, F maps every object Y to X and every morphism to the identity on X. Okay, boring, I don't know. That thing is called the constant functor. Delta X.
And the constant functor isn't unique because Y and X still aren't specified, right?
I mean, it maps every object Y of C to X.
Yeah, but it doesn't tell us how, so...
No, it just says, you give me any object of your category, I give you X back. You give me any morphism, I give you the identity on X.
Okay, but you do need to specify X then.
Yes,
right?
Yes, of course.
Okay.
That's why I
So
call it
there's
delta
a
X.
constant functor for each element X in D. Is that correct?
Yes, for every object
right.
D, X and D, yeah.
Yeah.
Okay, and now, after I've done these terribly boring examples, we get to the meat of category theory. Namely, what does it mean for something to be natural? And well, we can introduce a new category. Lol. Namely the category func. CD. So C and D are categories themselves. Can we define the category of functors? Well, The objects, okay, that's straightforward. The objects are, well, functors from C to D. Okay, that seems, I guess, okay. But now we have two functors. What are the morphisms between them? And I guess this is sort of a bad intrinsic motivation, but we will get there. We will get there. So how do we transform between two functors? We do it by means of what is called a natural transformation. A natural transformation between two functors, f and g, between two categories, C and D. Well, again, it consists of the following data. Well, we have two functors, and those functors operate on categories. So if we want to sort of map from F to G, we really only want to know what we have to do on the objects of C. So we really want, for every pair of objects, to have some morphism. So we have, for every object X in C, a morphism. Oh, we call our natural transformation eta. Morphism eta X. That is a morphism in, well, D, because F and G both map from C to D, between f of x and g of x. And we want them to satisfy some sort of naturality condition, namely, if x and y and C are objects, or yeah, are objects of C, and F is a C morphism from X to Y, then we have the diagram Fxy. So we have f of x and f of y, and then we have the morphism f of f going between them. The same thing we can do for g, just because they're all functors. So we have these things. But now we also have our morphisms from f of x to g of x, and from f of y to g of y. And we want them to commute. So that means that eta y after f of f is equal to g of f after eta x. And that puts a sort of hard condition on things. Okay, now okay. And I guess sort of important thing, such a thing is called a natural isomorphism. eta from F to G. It's called a natural isomorphism. If, well, it is an isomorphism, what does that mean? If there exists a natural transformation xi from G to F, such that, and well, I haven't really spoken about this, but we can compose them such that eta after xi is equal to the identity natural transformation on G, and xi after eta is equal to the identity natural transformation on F. By the way, I didn't mention it, but for any category, you can again sort of define isomorphisms, endomorphisms, automorphisms, monomorphisms, epimorphisms, whatever. And isomorphism just means there is another morphism such that when we compose them, we get the identity in both ways.
Okay, so can we look at the commutating diagram a bit longer, because we're now like 3 layers into categories and functors. So let's recap, I think.
So we have a functor F that turns every object of C into an object of D, and every morphism between objects of C into a morphism between objects of D. The same thing goes for G. So we have sort of this part of the diagram and that part over here. Now what we say is we want our sort of natural transformation between two functors to be, well, we have a lot of objects in C, a lot of objects in D. Namely, for example, f of x, g of x, f of y, and g of y. And we want our natural transformation to be just a morphism between f of x and g of x for every x. So sort of you list up all the objects in C and say, okay, I want now for every object in C, I want a morphism between f of that object and g of that object. And that is sort of the first part here.
Okay,
and this
just one question. I'm sorry, just one question in between. So we have eta of x, we have eta of y. Can you also have an eta of f that goes between the functors on the maps?
No. Well,
okay.
Let's say you could probably define it, but it's not strictly part of the definition.
Okay.
Yeah, and what this thing now says is, okay, we don't want just any sort of collections of maps between f of x and g of x. We want them to sort of be coherent. And that is achieved by this condition by saying that, okay, whatever map I have between x and y, I want this diagram here to commute, meaning that it doesn't matter in which order I apply f of x or g of x, or I apply eta. I hope this is going to become a bit more clear when I provide my examples.
I have one more question. That commutation relation, as you said, that holds true for all x comma y, right?
That should hold for all x and y, yes.
So you can say that this eta at the end of the day is like independent of any subscript x or y, or would that be an inaccurate
Well,
statement?
you say the eta is just the collection of all eta x for all the objects.
Okay. No, but can you say like some statement like eta x equal eta y or something like that?
No, because
No.
they are just completely different things. Like one goes from
fx to gx, the other goes from fy to gy.
Yeah, right.
So yeah,
like they're sort of maps defined on completely different sets.
Okay.
We're talking about sets.
Yeah.
Okay, and a natural transformation or a natural isomorphism is more or less what we mean in algebra or maths or whatever when we say this thing is natural. So this is where the name comes from. For example, the thing I maybe mentioned at the beginning, no, I didn't mention it. So we have k-vector spaces. And we have one functor be the identity, and the other functor be the double dual. So we map each vector space to, well, not the linear functionals on that vector space, but the linear functionals on that vector space. And
What's a k-vector space?
a vector space over the field K,
Oh,
think R or C or whatever.
all right.
And we say, well, we define a natural transformation eta by saying, well, eta on a vector space, well, what does it do with our vector V? It should map V to the evaluation functional in V. So meaning any linear functional gets mapped to phi of V. You can see that I can sort of write down this formula without any assumptions whatsoever on V. And this is always a good sign for naturality, because we can say naturality means that it is sort of defined by the same formula for every kind of object. I didn't really say much of why this is now a natural transformation, but it is a natural transformation.
No, this is what I meant when I asked you that doubt. Like, can we say that the map is the same, just like you wrote it right now?
Yes, in that sense, it is sort of the same because it is given by the same formula. Another thing that I looked up yesterday and searched for more natural transformations that aren't isos. We say C is commutative, or like, yeah, C equals D equals rings. Is that correct? No, that's not correct. We have C is rings, D is group. We have F is GL, N. So we have a ring and we just map, we just map a ring R to GLN of R, meaning the invertible n cross n matrices whose entries are elements of that ring. And what G does is, yeah, sort of cross. We send every ring to its ring of units. Then we have a natural transformation from F to G called the determinant. We just say determinant, well, for a specific ring, is just a map from GLNR to units. Well, what does it do to a matrix? It just calculates the determinant. Again, the determinant formula is a formula that is sort of doesn't really depend on the underlying ring, or that just doesn't care about the ring. So it is again natural, because you sort of don't have to do any choices.
Can you go a bit up again to the definition of isomorphism?
Yeah.
We didn't ask psi to be natural as well, did we?
Yes, it has to be natural. Okay. Very important.
Okay, I'm sorry, question. What is this R to the X that you wrote?
The group of units of R, so it is the elements that are invertible, that have a multiplicative inverse.
Okay. Oh, right, yeah, that's like the cross.
I'm just saying that if you sort of think of R to be the real numbers or the complex numbers, like the formula for the determinant is the same, and it always maps GLNR or GLNC to, well, an invertible number or a non-zero number, either in R or in C.
Okay.
Hi, so I also have a question. From this example, like, so generally for determinant, we don't need a group as such, right? Because it's just defined on a like GLN of R or GLN of C. I don't see why a group should be there.
What exactly do you mean by a group is there? Do you mean GLNR or
Like
RX?
to define a determinant, why do we need the notion of D equals group?
Oh, we don't need, like we don't need a group to define our determinant. It's just that sort of if we restrict the determinant map to the invertible matrices, then we get an invertible element of our underlying ring.
You somehow want the determinant to be compatible with the multiplication, I think.
Yeah. Alternatively, we can just say C equals D equals ring. Functor being, well, we map a ring R to the n times n matrices, and G being the identity functor. Then we have the same thing, I suppose. No, we don't. Because important takeaway, this thing has to be a morphism. So this thing is a group homomorphism between GLNR and RX, which, yes, is the case. We could weaken it by saying that like we have monoids or something, but please don't.
Okay.
In any case, maybe we take like a 5-minute break or something. Because this is sort of a thematic break. And I suggest that we reconvene again at 2:20. So now, after the break, we are going to delve into what category theory is sort of known for, namely constructions using universal properties. And this falls under the hat or whatever of limits and universal properties, I guess. And we are going to begin, what a surprise, with another definition. Let's see, be a category. An object x of C is called initial. If, well, I phrase it a bit weirdly, I say that for every other object, the number of morphisms between x and y is equal to 1. It just means that there is exactly one morphism from x to any other object. So if we draw our category like that, then X is initial if we sort of have maps from X to any other point in that category. Oh, Jesus. And moreover, these maps have to be unique. Not every category has an initial object. That's why I say. And of course, you can prove that the initial object is unique up to unique isomorphism. Yeah, I don't know, it's probably a remark I do after that one. Anyway, and it's called terminal, or final, I guess. If, well, there's not a morphism to every other object, but from every other object.
So if it's initial in the opposite category.
Yes,
Okay.
yes, thank you. And yeah, I guess remark, initial and terminal objects are unique up to unique isomorphism. Show objects. Proof being as follows: if X and Y, if X and X prime are initial objects, then we have a morphism because X is an initial object. We have a morphism F from X to X prime, and because X prime is initial, we have a morphism G from X prime to X. Now F after G is a morphism from X prime to X prime, and because I know I said every other object, but this really extends to X itself too. There's exactly one morphism from X prime to X prime, which is the identity. So, so is identity of X prime. So F after G is the identity of X prime. And the other way around. So this shows that F and G are isos. So, and since F and G were unique, this is the unique isomorphism part. And by reversing all of the arrows, we get the similar statement for terminal objects. As an exercise, I have now written down that find initial and final objects for the following categories, set, ring, group. I think it might be instructive to show at least one example. So set. From what set does there exist precisely one map to any other set?
Empty?
Yes. Yeah, for every set X, we have, well, the empty map going from the empty set to X. Okay, that is a morphism, and you can't really define any other maps on the empty set. Now for a slightly harder question, is there a terminal object?
You mean of set in general, or are we still talking about the empty set?
Of set in general.
Okay.
You reverse the arrows.
Sorry?
No, I was just joking. You can reverse the arrows.
No, doesn't work in this case because you can't map anything to the empty set.
And
No,
maybe
I know, that's why it's a joke. Yeah.
some singleton may work, just some constant map.
But which one?
Aren't they all isomorphic?
Yes, any singleton. Because, yeah, for every set x, we have the constant map from x to that point. And of course, every singleton is isomorphic to every other singleton by the constant map. And that isomorphism is also unique. Okay, the other exercise was to do this for ring and group. Do this at home, I don't know.
I'm sorry, one question. So the empty set is initial, but that means that you can map from the empty set?
Yes.
How does that work? Because you don't have any object to map from, right?
Yeah, that means you can have an empty function definition.
But a function requires something to be mapped on, right?
Yeah, but like you can have maps from the empty set. They just don't do anything.
Okay.
We haven't anything to map.
Yeah, like if you say, oh, what should f of x be? Oh, yeah, there is no f, so I'm done.
Do we require for ring homomorphism to map the one to the one if there exists one?
If we say ring is the category of unitary rings or unital rings, then yes.
Okay, and otherwise not. Of course.
Yeah, otherwise not.
Yeah.
Yeah, so for ring, you're going to get an interesting initial object.
This example would also work if you take your map from a singleton set to X, right? Instead of a null set.
But that's not unique. Like, can have the map from the singleton set to X. Yeah, sure, that sort of chooses an element of capital X, but which one? There are potentially multiple object or multiple elements of X. So
the same argument that they are all isomorphic doesn't work the other way around.
well, I mean, if you have two objects that are terminal, then they are canonically isomorphic, yes. But I don't know. Well, I guess if things are isomorphic, then they are also both initial when one of them is, but yeah.
So the zero ring isn't initial, or
The
why
zero
did you
ring
say?
isn't initial, correct?
Okay.
But it's final.
Yeah. Okay. Oh, I've actually done this as a lemma right afterwards, that they are unique, up to unique isomorphism, but never mind. Now, the idea of initial and final objects turns out to be very productive because we can reduce every universal property ultimately to some construction being the initial or terminal object in some weird constructed category. So yay for that. And now I'm going to give you the framework to do all of these definitions, to do all of these constructions in. I promise you afterwards we will do examples, and it's just going to be much easier, but still. Okay, we have, let I be a small category, meaning that the objects form a set. And let F be a functor from I to some other category C. then we define the category cone of cones by having the objects be oof. Okay, we have a pair n psi where n is an object of C and psi is a natural transformation from constant functor n to f natural. And a morphism of cones. Oh God, this is going to be nice. Between a cone n psi and n prime psi prime is just a morphism from n to n prime, such that it respects our natural transformations, meaning that psi prime I is equal to psi I phi for every object I and I. Yeah, this is, I already see Nicholas's concerned look. This doesn't really seem nice. So when we write all of this out, can you explain the definition of the objects of the cone again? Yes. So we have, so I've already sort of alluded to the fact that a functor on like a small category, we can see that as sort of a diagram in C, somehow modeled on I. And what now this cone means is that we have morphisms psi I from n to every object, particular to every f of I. So for every object in our diagram, such that when we have two objects and some morphism between them, that this thing here commutes. And well, then a morphism of cones is, yeah, sort of a thing that preserves that property. So for example, when we have the category, the discrete category with two objects, then the functor I just turns, Jesus. Functor I basically just chooses two objects, f1 and f2, for example. What then a cone is we have a map from n to f1 and to f2. And if we sort of have morphisms here, then this thing should respect this morphism. Yeah, I don't know. Secondly, we can define cocones. And yes, they are called cocones and not just nis. Yeah, this is basically just cones in the opposite category. So we have n psi, where n is an object of C, and psi is a natural transformation from f to delta n. Basically saying that we now don't have maps from n into our diagram, but from our diagram to n. And then we define the limit of a diagram F or functor F is a terminal object in cone F. And a co-limit of F is an initial object in cone F. So what does that mean? Well, on the surface of it, limit means, okay, it is sort of the universal cone. If we have any other cone, so if we have any other thing that maps to our diagram in this way here, then there is a unique morphism. So if we have another n tilde that also maps in this way, then we have a unique morphism from n tilde to n. And I guess the commutative, or I guess the people who did commutative algebra with me are already thinking like, oh, this seems somehow familiar. Like, I have something that maps in a way to some diagram, and for any other object that maps in the same way, I have a unique morphism. And yeah, sort of the dual notion would be mapping from that diagram into whatever m, and if I have another m tilde that also maps in the same way, there is a unique morphism in that direction. So it is sort of the template for our universal constructions, but really abstractly.
How do you mean the implication? Psi f implies delta of...
Oh, that is a notation for natural transformation.
Ah, okay. Okay.
F delta n, I think. Okay, I hope I haven't driven too many of you away by these definitions. For that reason, I'm now going to do a whole host of examples. Example 1, initial and terminal objects. Because, of course, if I bring an example, I will first bring the trivial one. Consider our category I to be the empty category. And, well, F the unique functor from the empty category to C. The empty functor, I guess. What is now a cone? So we want a natural transformation from, sorry, I always have to look this up. Want to have a natural transformation from, okay, the cone of F. We have n is some object of C. And this thing, psi, is a natural transformation from delta n to, well, the empty functor. So for every object in the empty category, we are given a map from for every I in the empty category, we are given the map psi I from n to f of I. Oh, okay, so this is nothing. our natural transformation is just nothing. So the cones of F are just the objects of C. Or I guess C. And similarly, co-cones, but we don't have anything to map from. So what's in the chat? Yes, for all E with E Widerspruch. Yeah, so we don't have anything to map from. So the whatever our psi isn't anything. So the co-cones of F are also just C. But then the co-limit of F is the initial object of co-cone F, meaning it's just an initial object of C. And similarly, the limit of F, or I guess a limit of F, is just a terminal object.
I'm sorry, you lost me at the natural transformations and all that stuff. I don't really see what the procedure or the meaning is here.
You mean with my example or with the definition?
Also in the example, I want to see how the example is worked out, basically.
Yeah, okay. So natural transformation from delta n to f. Delta n and f are both functors from I to C.
Yeah.
Yeah. So from the empty set to C. So such a natural transformation is given by, well, for every object of I, we have a morphism from psi I, well, from the constant functor n in I, which is just n, to f of I, such that like this condition, this naturality condition is satisfied. The naturality condition in this case reads like I to delta n j, sorry, small j, and then we have fi, and we have fj, and this is whatever the map between I and j we are looking at. But this thing here is just n, and this thing here is also just n, and this thing here in between is the identity of n. So this thing here turns into this diagram, n to f of I, n to f of j, and then we have a morphism between them.
But f and I and f and j also need to be the same, right?
No.
Because you're mapping from the empty set.
Yeah, that is a general thing. Now, because we are looking at the empty set, like for every object in the empty set, okay, we are done. Like this statement is true. Like you don't have to do anything to specify such a map. So this thing is always just, I don't know, the empty set or something. And this way we can say that, well, every cone is basically just given by an object in C, and that's it.
Okay. Okay, so let's just keep it like it is. Then how does that diagram lead us to the answer of the question?
It doesn't lead us to anything. Once we've noticed
we wanted
that
to find the cone, right, or something along those lines.
Well, I've just said that, like, this natural transformation, there is only one, the trivial one, or the empty set, or whatever, the empty one. So every cone is uniquely determined by the object, and conversely, for every object there is such a cone. And same thing for the co-cone. And now we've said that what's a terminal object of cone? Oof, always have to look this up. So now we've said a limit is a terminal object of cone f, but cone f is just C in this example. So a limit of f is a terminal object of C. And similarly, a colimit of f is an initial object of C. And this is exactly what I've written down here. So in this way, okay, initial and terminal objects also arise as limit and colimit of some functor. Okay, I guess. But this is just a small remark. More interesting example is the product and the coproduct. So we have I is the discrete category of the set 1 and 2. Meaning that, well, the objects of I are the numbers 1 and 2, and the morphisms between 1 and 1 are the identity. The identity is the only morphism between 1 and 1, and the identity is the only morphism between 2 and 2, and there are no other morphisms. So in a diagram, we would write it like 2 points, 1 and 2, with sort of the identities implied. Now, the functor f from I to some category C, well, what does it do? Well, it maps the points to things. So like we have two objects. F1 and F2 that are objects of C. And then in total we have two morphisms, namely the identity of 1 and the identity of 2. But the functor laws already say that we have to map them to the identity of F1 and the identity of F2. So the functor basically just gives you, is just given by F1 and F2, or I guess the choice of F1 and F2, and that's it. So if now we want to describe the cones and the co-cones again. So if n psi is a cone, that means that n is an object of C, and then we have two morphisms. Psi1 from n to f of 1, and psi2 from n to f of 2. And that's it basically, because sure, the identity gets mapped to some stuff, but we have no morphisms between 1 and 2. So our coherence condition basically just is always the case when we have two morphisms.
Just to be very clear, n and phi and psi are elements of the cone, aren't they?
The tuple n psi is a cone.
Is the cone itself and not an element of the cone? Okay.
Oh no, it's a cone. Meaning that when we have here f of 1 and f of 2, the cone is given by n psi 1, psi 2, and that's it. No conditions on psi 1 and psi 2. It's called a cone because we have sort of only arrows pointing from n to stuff, because this thing looks like a cone here. Similarly, if n psi is a co-cone, then, well, n is an object of C, and we have two morphisms. Psi1 from F1 to n, and psi2 from F2 to n. And again, that coherence condition just vanishes because we have no maps between 1 and 2, basically, because we chose the discrete category. So what does this look like? We have F1 and F2. And then we have N and just 2 morphisms. Okay. If we now have an so we have the limit of F is now the terminal cone. Oh, yeah, A limit is now a terminal cone. Meaning that the limit of F satisfies the universal property of, well, if, sorry, we usually call the object the limit, and then we are still given the 2 morphisms that determine that cone. And in that case, they're called pi1 and pi2. Is a terminal cone, meaning that for every n and morphism psi1 from n to f1, psi2 from n to f2, there is a unique morphism from n to lim f. Okay, that's just the terminal thing, but now what does it mean to be a morphism of cones? Well, it means that it sort of respects that property, meaning that they call it eta, that if we put pi1 after eta, then that is equal to psi1, and pi2 after eta is equal to psi2. Or in other words, can I put them both on the same page? In other words, if I have another object here with morphisms psi2 tilde and psi1 tilde that satisfy absolutely no properties at all, except for the fact that they are morphisms, there is a unique morphism between n tilde and that limit. Or let's say those 2 morphisms, psi1 tilde and psi2 tilde, sort of factor through n. And this means that lim f is the product of f1 and f2, because every morphism from anything whatsoever to the product of f1 and f2 is given by giving a morphism to f1 and a morphism to f2. And well, the dual construction to this co-limit of f is the coproduct of F1 and F2. Or I should really say a coproduct and a product, but they are unique up to unique isomorphism, so yeah, usually they're just considered to be the same. Would you like me to continue with 2 more examples, or should we leave it for the day?
I have to go pretty soon, but you don't have to stop because of me. Just continue and I'll look the video.
Continue, maybe, yes.
Yeah, I guess if anybody wants to leave, they have always had that opportunity. So yeah. Okay, so although we are probably not very used to arguing about products and co-products in terms of those universal properties, they are exactly what they are defined as. And to be fair, like this is seems to be still quite a simple thing. I mean, we're working with a discrete category, imposing no conditions.
Okay, question. I don't really still understand this delta notation with the delta n that we used in these cone questions.
Yeah.
Yeah, I don't know, it didn't hit me when you first wrote it down, and now I see you writing it again and again, and I don't know what it means.
Okay, so that delta, that was the constant functor.
Constant functor.
So it maps every object to n, and every morphism to the identity on n.
And n is an object of C.
Correct.
Everything goes to n.
Yeah.
Okay, okay.
I mean, I could have given a more hands-on definition of cones and co-cones, but that, yeah, it's basically sort of for every object, you have a morphism from n to that object, such that things work out nicely. Okay, bye, Jakob. But I find that this at least is a sort of concise definition, even though it's not immediately obvious what it means. And I mean, until now, the naturality condition hasn't meant anything because we have never had to impose it really in the examples we've seen so far. But this will change because we are now going to discuss fiber co-products. So, and this is the point where I'm just going to write my categories as images. We have as I the category, well, we have an object called 2, and an object called 1, and an object called 3. And we have a morphism from 2 to 1, and a morphism from 3 to 1. What does a functor do now? So F is now, okay, we have 3 objects. So we have F1, F2, and F3. Those are all objects of C. And then we have, well, 2 morphisms, one between 2 and 1, and one between 3 and 1. So we have morphism between F2 and F1, and a morphism between F3 and F1. And I'm basically going to phrase everything concerning F using that data and not necessarily using F. So if we now have a cone, that means we have, well, we have F2, we have F1, and we have F3. And between them, the morphisms F and G. And then we have another object, N. And so that's the object part, and the natural transformation consists of a morphism psi2, psi1 and psi3, such that, well, this diagram has to commute so that means that G after psi3 should be the same as psi1, and similarly F after psi2 has to be psi1. So to be fair, psi1 is completely determined by all the other data. So n psi is determined by psi2 and psi3, which are morphisms, from n to f2 and f3, such that G after psi3 is equal to F after psi2. So, and now again, we take a look at what does it mean for something to be the limit of that diagram. So limit F is a cone. So we will have the set limit F, or not the set, the object limit F, and then two morphisms. Let's again call them pi1 and, pi2 and pi3. And it satisfies for every other cone given by an object and two maps to F2 and to F3, such that G after psi3 is equal to F after psi2. There is a unique morphism from n to lim f eta, such that psi2 is given by pi2 after eta and psi3 is given by pi3 after eta. Or in other words, if we have this diagram here, let's just erase that thing here, and we have another object n tilde, and we also have a map to F3 and a map to F2, such that this diagram commutes, then there is a unique morphism from n tilde to n. And since we sort of have this extra condition, I mean, it still looks a bit like a product. Sort of a map to N is given by a map to F2 and to F3, but it has to satisfy some condition. And this is the reason why this isn't called a product, but a fiber product. Lim F is the fiber product of F2 and F3 over F1. And if you use the dual or the opposite category, then you get the fiber co-product. Using IOP, define fiber co-product. And since this construction might not be as known as the product to everyone, I'm going to quickly write down what this means for sets. So if we have two sets, X and Y, and we have maps from X to S and from Y to S, then this fiber product is just defined as the pairs in X, Y, such that f of X is equal to g of Y. Sort of X, Y, where those two maps here are just the projection maps. That's why I called them pi before. And those maps here are F and G. And if we now have any other sets N with maps to X and Y such that, well, F after this thing here is equal to G after this thing here, then we get a unique morphism to the fiber product. And the last example, which I'm probably not going to discuss, so maybe I can just hint at it. So we have done sort of simple diagrams, but what if we have two morphisms? What are the limits and the co-limit of that diagram? And it turns out that the limit is called equalizer of those two morphisms, and the co-limit is the co-equalizer of those two morphisms. And that is sort of the more abstract notion to the kernel and the co-kernel.
Philip, just one question here.
Yeah.
So you defined all these cones, and the idea is that there will be this limit which will be the terminal point. Hello? I heard something else.
I don't know.
Okay, so the idea is that there will be this limit which will be this terminal point, but how do you determine what it is? For example, here I could have even defined the limit to be n, right? And there will be unique morphism that goes the other way around too, right? Like which one is the fiber product?
This thing here is the fiber product. And
but how do you define it?
Is, I mean, usually you have the sort of fiber product is this abstract categorical notion of, well, the thing that satisfies this universal property. And you can just define the set here and show that it satisfies the universal property. And this then shows that, yeah, set has fiber products.
Okay, but there is no unique fiber product as such.
I mean, it's unique up to unique isomorphism. And that is really all you can hope for in category theory. But like unique as this is the only set and there's no other like it. No, you don't get that.
Okay.
And I also didn't explicitly mention it, but of course, categories don't have to have initial and terminal objects. And therefore, functors don't have to have a limit or a co-limit.
Yeah.
And therefore, products, co-products, fiber co-products, equalizers, co-equalizers don't have to exist. It's just that, for example, set is a very nice category, and in set, those things all exist. But that is something that you have to show that is not obvious in and of itself.
Okay. Yeah.
Okay, so yeah, equalizer and co-equalizer is sort of the more abstract notion to kernel and co-kernel of a map. Do with that information whatever you want. Apart from that, I believe I'm done.
Nice lecture.
Yes.